Okay. Now, just let me remind you what we discussed until now. We started this topic, which is power electronics, by discussing rectifier first, then DC-DC chopper, and we completed also inverter. The last circuit to be discussed here is the AC voltage controller. What we have is AC. Okay, you know what we have as example in Oman. One second. We have AC 230 volt, 50 hertz. This is input, and output, okay, is my load here. The converter in between, which convert this AC into AC also, but in another voltage, frequency, both. We call it AC voltage controller. Now this circuit used to control AC loads. AC load could be anything, and you know most of our loads are AC. Talking about as example in industry, we're talking about industrial heat, on load transformer connection load. By the way, changing. By the way, we will discuss these applications later on, inshallah, when we approach the applications. Or we can control light, or we can control induction motors, or AC magnet. These are large applications in industry. You know, as example, light, to control light in the past, they use variable resistance. Okay, in this way, or transformer in this way with center tabs, tab 1, 2, 3, 4, which is large. Today the controller is a small, very small circuit chip, a small chip contain this AC voltage controller. We control it, control, as we will see how we control it later on in our discussion. But we control it, we control the output voltage, and then we control the load operation. Example, another example, controlling the induction motor. You know, when we change the speed of the induction motor, the function will change. How we change the speed? By changing the voltage, one of the ways. Now this circuit can be classified into two types. One of them is on-off control, and the second one is phase angle control. We will discuss both. And also based on phase, we can control them in single phase and three phase. And also based on the control type, we will classify them into half wave and full wave. It's clear. Remind me with rectifier, half wave, full wave. Half wave when we have one switch, full wave when we have two switches for the two parts of the waveform. Now let me start with the phase method, with the phase circuit, which is on off. From the name on off, it means it will be on for a time and off for another time. How it look like the circuit? Have a look here. This is my voltage, input voltage. Let me say 230, 50 hertz. And this is my load. Let's assume first is resistance. The circuit is very simple. Two thyristors or switches, transistor, whatever they are, connected anti-parallel. Anti-parallel means opposite direction. Okay? One of them to control the positive part, and the second one to control the negative part. Now, how we trigger them? We trigger them at angle 0. It means alpha for this one is 0. For this one, alpha is pi. It means at 0. I mean here, here, here. It should look like it's work as a diode. Okay, what is the point? We will not switch them for the whole time. No, for some cycle they will be switched, and for some cycle they'll be off. Let me show you here. This is my input, and this is my output. Here I switch, you see here, gate 1, it means thyristor 1, gate 2, it means thyristor 2. I switch thyristor 1, the voltage appear across the load. Switch here, thyristor 2, the voltage appear across the load. And again, thyristor 1, thyristor 2. Here I did not switch anything. They are off. There is input, as you can see here, but the output is 0. I repeat itself again and again and again. Now let me call this here, from here to here is n number of cycles. And from here to here is m number of cycles. So n is the number of cycles we have on, and m when we have it off. Now, if I come to integrate to find the output of this voltage, the RMS voltage output will be 1 over 2 pi the full period. Okay, integration from 0 to 2 pi, maximum voltage square, and square root here. But I will do here something. I will multiply number of cycles per number of cycles on and off. Okay, in this way I can find the output voltage, which is this one now. From here to here. This is my cycle. Now I did the integration. What I come up with is output voltage is input voltage times square root n over n plus m. What does this mean? This means by controlling هنا m, I control the output voltage. Then I control the operation of the load. If it is a light, if it is induction motor, whatever it is. Now let's use this in example. An AC voltage controller in the previous circuit has a resistive load. He gave me the resistance 10 ohm. And root mean square value input voltage is 120, 50 Hz, 60 Hz. Thyristor switch is on for 25 cycles and off for 75 cycles. Determine the RMS output voltage. We have formula. The input power factor, which will be at the end, output over input. And average and RMS current of thyristor. Okay, I have everything. He gave me R, he gave me VS, he gave me, definitely I can find VM by multiply by square root 2. The constant K, which is n over n plus m, I can find it now because he gave me n and n. Now I come to work. VS is given, n over m plus m is given, so I got the voltage. Output voltage is 60. If I divide it by the resistance, it gives me the current, ohms. Output power is V out square over R, or I output square R. Both will give me 360. Now next is to find the input, because I need to divide them. P out over PM, VM, V volt ampere of input. Input voltage is 120, he gave it to me. And input current, it will be assumed the same current, because we usually deal with the circuit as ideal circuit. I mean lossless, the same current input, the same current output, which is 6. I have the input volt ampere. When I divide them, 360 over 720, it will give the power factor. Usually this circuit has low power factor. Sorry. And losses is small. Losses, sorry, is high, So this circuit is useful mainly for application where the load is not important to consume I square R or V square R. What does this mean? It's preferable to use it to control induction heating, as example. Oven. But not that much preferable to be used for controlling motor. Why? Because we have winding. It will be heated, and if it's heated, it will be burned. Either we reduce the life period of the motor, or it will not work efficiently. The other method to be discussed soon is more useful than this one. Now, last one is to find the current of the thyristor, average and RMS. Okay. Now, thyristor, each thyristor will work for pi only for half of the time, from 0 to pi. The current would integrate with respect to t. Again, every 1 over 2 pi. And don't forget to multiply by n over n plus m. We got the current. We have everything. Just need to substitute. For RMS, the same previous one, just we added here in this way, 1 over 2 square root 2, and all this part to be square, as you can see here. Also, we do the calculation. We have the RMS current. Now, the previous method, on and off. The new method is phase control. In the previous method, we trigger the thyristor at alpha 0. Now we will trigger it at another alpha. It could be any value, not 0, any value. And let me start in this simple circuit, which is half wave. We can see one switch, but here we have diode only. It's clear for the diode, the negative part will be conducted by the diode, voltage and current. But the thyristor T1, when we trigger it from here to here, you see, this is alpha, the input will appear across the output. This is how it looks like. Increase or decrease alpha will change the output. Very simple and clear circuit. By the way, it seemed to be, when we discuss this AC voltage controller, there is some sort of similarity with rectifier circuits. Yes, you're right. Now, when we come to find the output voltage, we will integrate for thyristor from alpha into pi, but for diode from pi into 2 pi. This is input voltage square. By the way, all of them divided by 1 over 2 pi because of the period, and we take square root here. Now, remaining is integration. We convert sine square into 1 minus cosine. We integrate, we got formula. We need the formula. Formula contains Vs and alpha. You have alpha, you have Vs, you can find it directly. What about average or DC? DC or average, the same previous equation, but without square root and without square. Directly from alpha to pi, input voltage, pi to 2 pi, input voltage. And we have another formula. Let's apply this example. By the way, it's almost the same example, the same procedure, just the circuit difference. I mean, when change, the equations we use is different. Okay. A single phase AC voltage controller has a resistive load R given to me 10, and the input voltage Vs is 120/60, the same supply. The delay angle of the thyristor alpha triggering angle is pi over 2. Again, determine RMS output voltage, the input power factor, the average input current. Now, let me check the information. He gave me R. He gave me Vs. He gave me alpha. I can find Vm by multiply by square root 2. I have everything now. Let me come. Now, let me take you back just here. This is the formula. I will use it. I use it. I got the output voltage. Output current is V out over R according to Ohm's law. And P out is V out square over R, or I out square R. We got it. And volt ampere will be Vs Is. We have Vs given in the question, 120. Is is the same current, which is 10.39. I got the input volt ampere. Now let's divide them. We divide them. We found the power factor. Now it's improved, by the way. We found the power factor 0.866. For DC, let me take you back to the formula. This is the formula for DC voltage. I substituted here, as you can see. By the way, it's found to be in minus. Why in minus? Just a minute, let me take the graph. You see the graph here? The minus part greater than the plus part. When I do the average, definitely it will be minus, as you can see here. Now the current, the diode current will be VDC over R. So I just divide it. Now let's improve the circuits. Let's take now full control or bidirectional, they call it, or full wave. You can see now I have thyristor here and thyristor here. No more diodes. The first one, the first thyristor is the clear. We discussed it in the previous circuit. But the second one, also again, you see here, at pi plus alpha, I triggered. What I got the input appear across the output. So when we integrate now, we don't need to integrate both. One of them is because they are, let me say, similar one, symmetrical, let me say. So 1 over pi from alpha to pi, square the voltage and integrate and then take the square root. We have formula, another formula, as you can see here. We can use it. Now, this previous circuit, we can have some other circuit which gives the same function. As example, this one. This one here, we have 2 diodes and 2 thyristors connected in this way. They gave this circuit gives the same effect of the previous circuit with 2 antiparallel thyristors. How it works? When we have positive signal, current will come from here through this side, this thyristor T1, and through diode. This is the right way. And back. Let me change the color. When negative part coming, current will follow here through this thyristor, this diode, and back to the supply. You may say, okay, why we did this modification? What is the point? The point is, rather than we have firing circuit here or triggering circuit for this one and for this one, another one, we will have one circuit trigger both at the same time. But the thyristor which is forward bias will conduct. As example, when it is positive, it's trigger thyristor 1 and 2, but thyristor 1 will conduct only. So we reduce, the cost, because we have now one firing circuit. But from the other side, we increase the losses. Why? Because here, at any instant of time, 2 switches are conducting. As example, when it is positive, thyristor T1 and D1 in series, and they conduct the current. So losses on and drop on D1 and T1. When it is negative, the drop will be on D2 and T2. Another modification, we use here 4 switches beside the thyristor. By the way, either we use transistor or thyristor, it doesn't matter, but one of them. But 4 diodes. How the circuit work? Have a look. In positive, current will follow here. Definitely it will take this path, then diode D2, then back to the supply. When it's negative, as you can see here, current will follow here through diode D3, again thyristor D4, and back to the supply. Definitely this circuit will give the same output, but at the same time we have 3 switches conducting at the same time. As example, for positive, we have D1, we have T1, we have D2. So more drop across the circuit, more losses. However, the thyristor will see the voltage and current following in the same direction or the whole time, either if it is positive input or negative input. But the output is the same. The output, just to remind you, is similar to this one. This one and this one. Now let's take it an example. Have a look, have a look. A single phase, full wave AC voltage control. We need always to read carefully the name of the circuit. Single phase, I understand that it is one phase. Okay? Not a three phase. Full wave, I understand two switches, T1 and T2. AC voltage controller, I understand it is not rectifier, not DC-DC converter, not inverter. So by reading the name, you understand which circuit we are talking about. Resistance is given to you 10 ohm, VS 120, frequency 60. Both alpha 1, by the way, T1 and T2 is preferable to be triggered at the same angle. And this is what happens usually in industry. They trigger, there is no mean to have different angles. Okay. Now again, find the RMS output. You see, it's like the same example, just we change the circuits and we change the information. Calculate RMS output voltage. We have formula. Input power factor. We have formula. Average current for thyristor and RMS current for the thyristor. Now we calculated output voltage. We have formula. I just remind you here. And this is the formula. Now divide by R. We got the current. You see, it's procedure. P out is I out square R. I got the power. Volt ampere, Vs given 120, current is the same. So I got the output, the input power. Now divide them, I got the power factor. Now for the current in the switch, in the thyristor, we will integrate it from alpha, as example, thyristor T1, from alpha to pi, because the other half part will be 0. 1 over 2 pi over R, because we are talking about current now, not voltage. This is voltage divided by R, it will give current. Integration of sine minus cosine, substitute, and then we go this formula. What we have in this formula? We have Vs is given in the question, R given in the question, alpha given in the question. Just we need to substitute. We got the current. For RMS, we repeat the same discussion here, but squaring the voltage and taking square root 2. We need to convert this from sine square using trigonometric integration by trigonometric from the table. And then we got the integration and the formula here. Again, the formula contains Vs, R, alpha. We have all of them. We just need to substitute to find the current. I will stop with this circuit to be continue in the next session. Just 1 second.